I was reading Evaluating Interesting Integrals and came across this mad way of evaluating the Gaussian integral. In order to show you this mad way of evaluating it, I think it's nice to first show you this little lemma. It's not really a lemma, but I think it's nice to get a reminder of these things every so often. So let's say you're given a function of this form, where it's an outer function applied to an inner function, evaluated from 0 to x. Integrated from 0 to x. How do you take the derivative of this function with respect to x? Well, of course, we can just use the chain rule and take the derivative of the outer function and multiply that by the inner derivative. This inner derivative may seem a bit difficult to calculate. Do we actually need to take this integral? Well, of course we don't, because what is the integral from 0 to x of some inner function? It's just the antiderivative of that inner function evaluated to x minus the antiderivative at 0. Taking that derivative with respect to x will, of course, just lead you back to the original function. So that's how you take the derivative of that kind of function. And of course, I will remind you that this is the Gaussian integral, the integral from 0 to infinity of e to minus x squared dx. Next, I will remind you of Leibniz's rule. So if we are given an integral of this kind, I of x and t is the integral from a of t to b of t of f of x and t dx, we can take the derivative with respect to t in the following form. Now this might seem a bit unfamiliar to you, and that is completely fine, because usually we don't really have variation of the upper and lower bounds, and in that case this whole part just goes to 0, and you will have it in this more familiar form, which you may know as Feynman's rule of integration. But of course Feynman did not invent it, he learnt it from some other calculus book. So let's define our two auxiliary functions, and what we're going to do in this method is going to take the derivative of both these functions and show that they exactly cancel each other out, so that the sum of the functions is a constant. Then, as x goes to infinity, we'll see that one of these functions, specifically g of x, will go to 0, which will leave us with just f of x, which will easily show us what this integral is. This is a bit of a silly way of integrating a function, and of course you only do it once you know the actual answer. I don't think you would ever use this kind of method to solve for an integral you didn't know already. But it's a fun method. Well, what's the derivative of f with respect to x? I promise you to be exactly the opposite of this derivative, and it will be. So first we take the outer derivative, derivative of something squared is 2 times that something, times the inner derivative, which we said is just the inner function. So it's 2 e to the minus x squared, integral from 0 to x, e to the minus t squared dt. What's the derivative of g with respect to x? Well, since we said that the boundary of integration are constant, this whole part falls away and we don't care about it, but we do care about this part. Partial f to partial t. Well, here actually we've taken it the other way around, where partial f will take with respect to x, and the integral will be with respect to t. So, taking the derivative with just respect to x, where t is a constant, we see that this is the derivative of e to the minus x squared times some constant, which is of course minus 2x times that constant times e to the minus x squared times that constant, all over 1 plus t squared, because that's just what we have inside the integral. And look at this, in the numerator and denominator we have this same expression, so they cancel each other out. So this is minus 2x e to the minus x squared, integral from 0 to 1, e to the minus x squared t squared dt. This is also very reassuring. Why? Because, of course, we've shown here that partial f to partial x, in this case, is bounded. And why does that matter? Because in order to use the Leibniz rule of integration, we would have to show that this inner partial derivative is bounded. If not, then the whole thing falls apart. And you can see that if you go over the proof of Leibniz's rule of integration. Well, it doesn't actually have to be bounded, it has to be dominated, which is a much weaker condition, but usually boundedness is much easier to show, and in this case it is bounded indeed by 1. So, to evaluate this little integral, we will substitute u is equal to dx, so du over dx is dt. Of course, x here inside the integral is just a constant, so we can do this with no fuss. Evaluated u at 0, 0, u at 1 is x, and we get that dg to dx is minus 2x e to the minus x squared, where of course if you take e to the minus x squared outside the integral, because again x is constant with respect to this integral with respect to t, e to the minus t squared d over x, where again x is constant, so it just pops out. So this is minus 2 e to the minus x squared, integral from 0 to x, e to the minus t squared dt, and what a massive coincidence, this is exactly minus df to dx, like I promised you. So dg to dx plus df to dx is 0, which implies that g plus f is a constant. What exactly is this constant? Well, since I told you that g is going to go to 0 as x goes to infinity, you can already guess, since you know what the value of the Gaussian integral is, but we're just going to show it. Evaluating these both at 0, well, f at 0 is 0, So we just end up with g of 0, y is equal to 0, 0, because of course it is the integral from 0 to x of something squared. It doesn't matter, from integral from 0 to 0 is of course 0. So this is just g of 0, which is the integral from 0 to 1 of 1 over 1 plus t squared dt, which is the arctangent of t, which is pi over 4. So, now, the limit as x goes to infinity of g of x plus f of x is the limit as x goes to infinity of g of x plus limit as x goes to infinity of f of x. And we can, of course, interchange the limit and the integral here. Why can we do that? Again, because of the boundary convergence theorem. Again, well, we can say the dominated convergence theorem. It doesn't really matter. These functions are, if you take them as functions of t parameterized by some index n, then these are obviously all monotonely decreasing. So you can monotone convert, well, whatever, the opposite of the monotone convergence theorem. These are all obviously bounded by 1 over 1 plus t squared, so we can of course interchange the integral and the limit, which will tell us that the limit as x goes to infinity of e to the minus x squared to some constant is obviously 0, so this whole part falls away. This will just be the limit of x goes to infinity the integral of 0 to x e to the minus t squared dt squared. Taking the square root of both sides, we'll end up with the integral from 0 to infinity of e to the minus t squared dt is equal to pi over 4. And of course, taking the square root, we'll get that the integral from 0 to infinity of e to the minus t squared dt is equal to root pi over 2. And that's it. That's a crazy way of evaluating the Gaussian integral.